So, let us continue our discussion on mechanical equilibrium. So, in the previous lecture we started discussing a problem of cables and we discussed a little bit about what are the the nature of the tension force, and we reviewed critically about three particular assumptions that, and we are going to now do a problem where we will use those assumptions. So, the point here is that the normal assumptions that you make about rope and tension force in textbook problems, you have to see whether they are really valid in real life situations. So, let us start by defining our question. So, we are taking a class of problem which are called suspension cable. Now, this is a vast topic, and those of you who are taking various engineering course such as mechanical or civil engineering, you will learn a lot about this problem in your respective engineering course. From physics point of view, so I am going to pick up a selected subset of questions, and this is what I want to discuss. So, imagine that you have a cable which is hanging between two ropes, two ends, such as, for example, let us say this is a cable which is hanging between two support. So, the two support which are fixed. Now, what we know are the external forces. So, imagine that you are hanging clothes, for example, on a rope, or it could be some suspension bridge. So, there are external forces on the rope, and you know those forces. You also know the end to end length. So, this length from this end, suppose this is the end, this is the end, you also know the end to end length. And you also know what are the force boundary conditions. So, we will clarify what is boundary condition very soon. So, basically you know what are the details of at the end, the forces acting on the end, for example. And then we are interested to know about some simple questions, like, for example, what is going to be the shape of this rope if it is supported hanging between two fixed ends. So, which means that for example, what will be the curvature, so the local curvature determines the shape of the rope, and we will also discuss something called sag and span. And the other practical question that may be interesting from, especially from engineering point of view, is what is the tension in the rope. Now, I will say a little bit about the external loads. So, in general they can be point load which are applied at discrete points, such as there are three loads, four external forces, vertical forces F1, F2 and F3 in this picture, or there could be a load which is applied continuously along the length of the cable or the rope. So, we are going to assume that in this particular problem we are going to assume that this is the case. So, now let us define the example more concretely. So, as I mentioned, so these are two ends which are fixed, and these two ends A and B, and there is a cable whose length is L, which is hanging between two ends. Note that these two ends in general can be at different heights. So, they need not be symmetric. So, a flexible, and we discussed why do we need flexible a flexible cable in the previous lecture, and we are going to assume in this particular example that the cable is massless. So, one of the goal of this problem is to study the effect of mass of the cable in the analysis. So, in this example we are going to study a massless cable which is simpler, and in the next example we are going to add the mass of the cable in the analysis. Now, there is an external vertical load W per unit horizontal length. So, this is a continuously applied load, which is, let us say, represented by this horizontal red line, which is applied everywhere, and the amount of the load, so this is a load means a force, is W per unit length. Now, it is given that the structure is static, it is in equilibrium. Then the problem is determine the shape of the cable. So, if this is my, suppose this is my origin and I draw an horizontal line, which is my, take my x axis, and then I take this is my y axis, then this cable makes a curve which is y as a function of x in space. So, the question asks that what is this function y as a function of x. Now, one thing I want to emphasize here is that note the way I have chosen the coordinate system. This is not random. So, I have chosen the lowest point of the rope as my origin, and then I have chosen the tangent to the lowest point as my x axis and the perpendicular direction as my y axis. So, this is a deliberate choice to make the shape the equation of the shape as simpler as possible. And as you can expect in general that if you shift the origin, then the equation of the curve will shift, will also change. Okay. So, let us try to analyze. So, first thing is what is going to be our system. So, I am going to take our system as a piece of the rope. Let us say this is my rope or cable with some, so it has is a small piece. So, we expect that we are anticipating that the answer is given by some sort of a differential equation. So, we are going to take a small piece. So, let us say the length is dx, the horizontal length is dx, the vertical length is dy, and this length is dl. So, it is a small piece of rope, and this piece makes an angle theta with the horizontal, with the x axis. Then this is the tension. So, this is my system and everything else is surrounding. This is my system and everything else is surrounding, which includes the other parts of the rope. So, now we define the system and chosen the system and surrounding. Now, we look at the interactions. What are the forces? Now, the system is interacting with the neighboring part of the rope. So, there is a tension force on this side, and it is also interacting with the contact force with the neighboring part on the left side. So, there is also a tension force, and in the last lecture we saw that the direction of the tension force is known, it must be along the tangent of the rope. However, since this system is not horizontal, it is the tangent direction is continuously changing. So, these two forces are not in the same direction, which means they are not the same force. So, let us call that force T a theta, and then at this point, at this end, the angle with the horizontal is no longer theta, but T plus some delta theta or d theta. This is crucial. Now, why they are different? You can easily see that because this force on the reason if we look at the force balance of this slice of the rope here. Now, there is another force. So, these are T theta and T theta plus delta theta as shown in the picture, and also the vertical force. So, there is a vertical force which per unit length. So, this is a vertical force in the downward direction. So, that means that if we look at the so this force on the right hand side must balance not only this tension force on the left hand side, but also the vertical force, and that is what makes the tension non uniform in this case. Remember our discussion from the last lecture. Okay, so these are the interactions, there is no other interaction. So, I am going to assume that the rope is massless. So, there is no interaction between our system with the earth. So, these are only all the forces we have listed. So, now we are going to write down the condition of, so the whole system is mechanical equilibrium. So, the third step is to write down the condition of force balance, the mechanical equilibrium. So, let us say first we look at the force. So, let me draw the picture again. At this end, this is theta, this is d theta, this is d theta plus d theta, there is a force W times dx. Note that this W is a load per unit horizontal length. This is a crucial point, we will come to that. So, then what is the total force on the horizontal direction? So, this force has a component. So, this is theta plus d theta. So, there is a force T cos theta plus d theta minus T cos theta. Now, W is a vertical force, it does not have a horizontal coordinate component, and this must be 0, that is the condition of force balance. Similarly, let us write down the condition of, let us call that equation 1, and then equation 2 is the force balance in the vertical direction. So, we have the sign component of the So, let us take the equation 1 and simplify it further. So, let us apply the formula for cos A plus B. So, we get cos theta times cos d theta and minus sin theta times sin d theta minus cos theta. Sorry, I made a mistake here. So, this force at T plus theta plus delta theta, so this magnitude should also be different. So, let us call that, and magnitude has to be different because of the presence of this horizontal force. So, let me okay. Now, simplify the equation 1, then what we get is that now if we take a small piece, then the difference in angle between at left hand and the right hand are infinitesimal. So, we can approximate this to be 1, and the sine of d theta we can approximate by d theta. With this approximation, what we get is Now, for the first term, this t cos theta and this t cos theta will cancel. So, we will have dt times cos theta. In the second term, so we have this t times sin theta d theta, and the last term will be dt times sin theta times d theta. So, there are product of dt times d theta. So, that is a second order differential product of two infinitesimal. So, we are going to assume that that will be 0 because it is a product of two infinitesimal. So, then we can write the left hand side as now. Note that this I can is same as saying that the differential of t cos theta is 0. That means that t cos theta must be a constant. Let us call that t naught. Now, let us take the vertical equation. So, let me write down this picture again. Now, what we had is t plus dt sin theta plus delta theta minus t sin theta minus w dx is equal to 0. That was equation 2. Now, this gives in the similar way, if you expand this sin theta plus d theta in the formula of sin a plus b, and then assume that cos d theta is 1 and sin d theta is d theta, and dt times d theta can be ignored. Then this first two term represents the change in t sin theta, and it shows that this is equal to w dx. Let us call that equation 3, which means that d dx of t sin theta is equal to w. Now, let us assume, let us reflect what we have done so far. We have applied the force balance conditions and we got, let us call that equation 3, and we got this condition. Now, in the given problem, it is given that this w is constant. So, to emphasize that, let us call that w naught, but note that in general w can be a function of x, but in this problem it is given that w naught is constant, it is a constant force load applied per unit length. Now, the other thing is that again in this problem we basically have derived two equations. One equation is d from the force balance condition, we get this equation that this is 0, from which we get that the horizontal component of the tension force is constant, and we get another equation which is about the vertical component of the tension force, which is equal to w naught. But so in this case there are three unknowns. So, t is an unknown, and we also have theta, which is an unknown. So, the problem asks you to calculate the y as a function of x, which represents the shape of the cable. So, we need to eliminate theta. So, we need to eliminate theta and replace it by y. Now, how do we do that? So, note that there is a very simple, there is a simple geometric insight. So, if I look at this piece of the cable, and this has a length which is dx and it has an elevation which is dy, and this is the angle theta. So, then from geometry we see that tan theta is equal to dy dx. The other thing is that the forces are along the tangent, the tension force is along the tangent. So, tension force, the horizontal component is, let us say at this end, this is t cos theta and this is t sin theta. So, tan theta can be written as so, this is the crucial fact that a tension force is along the tangent. We can exploit this fact to replace eliminate theta. So, how do we do that? So, this is now the vertical component. So, what we have got is that the horizontal component is there is a differential equation in terms of with respect to the vertical component of tension. So, you take this equation this one and take a derivative with respect to so let us do it here. So, we have this t sin theta divided by t naught. Now, if I take a derivative of this quantity, so this is let me, so what I am writing is this point, this equation. So, we had tan theta is equal to dy dx and this is equal to t sin theta divided by t naught. Now, if I take a derivative both sides, with respect to x, we get is equal to now t naught is a constant. So, we can take it out and ddx of t sin theta is w naught. So, we get an differential equation that so we have a differential equation. Now, we can solve it to determine y is a function of x. So, let us do that. So, first let us take one now here is where, as you know, that in order to get a particular solution of a differential equation, you need some condition. So, here is where you need the boundary condition, because there will be constants of integration, and to determine those constants of integration you need some conditions. So, we are going to assume that this is where our choice of reference system comes in handy. So, at x equal to 0, y is equal to 0 and the slope, the dy dx equal to 0. So, this is our boundary condition. Now, if we get integrated both sides, we get w naught by t naught times x plus some constant c. Now, at x equal to 0, dy dx is 0. So, this means c is 0. So, we have dy dx is equal to w naught x by T naught. Now, then again you integrate, you get and some another constant of integration. Now, you apply that at x equal to 0, y is 0. So, which gives that C 1 equal to 0. So, you have W naught by T naught x square. So, this is the shape of a massless cable which is hanging because of some external load and supported at both ends. Now, once you have some relation, the first thing to do is to check whether this relation makes sense. So, here is a simple change, and for that you need to take some simple limiting case and see whether this makes sense. So, the simple limiting, what could be a simple limiting case? Suppose that there is no external force, that is W naught equal to 0, the load per unit horizontal length is 0. So, in that case your equation is just y equal to 0. So, in that case we expect that the rope is a massless rope. So, there is no absolutely no horizontal force, then you expect that the rope should be perfectly horizontal, and we indeed get a solution y equal to 0, which represents the x axis. So, our solution is indeed gives us back the is matching with our expectation. So, this solution, which is a parabola, makes sense. Our next goal is to now we are going to put the effect of mass, we are going to include the mass in our calculation and see what happens. So, that will be the topic for next lecture. Thank you.